And it wasn't that they were just simply dribbling at the same rate, because if they had just come back in, we wouldn't necessarily see it. We could possibly see it at the zero lag, but that would be highly improbable.
They came back into phase.
They came back into phase at the zero lag. Okay, so this is the observed network that we actually observed between our 7 participants. And this is just an initial study. This is one of those things that we've gotten the initial data and now we apply for grant funding. But what's really interesting about this is, remember we did that social questionnaire. And all of the literature says that socially paired dyads should synchronize. We did not find that at all. Only 2 of the dyads that we found as synchronizing had any social rapport. Okay? So a majority of them did not have it. So that's really interesting. Now, one explanation could be, what we did find was that the people that did not synchronize had much longer frequency. So they were dribbling much slower. Okay? So if we look at the previous literature, they had them doing very simple fine motor movements. They would have 2 people staring at each other and move an index finger back and forth, okay, between 2 lights. Okay? This is a much more gross motor movement. It requires a little bit more of the participants. So possibly what this is saying is that people that are very close in motor patterns may be synchronizing easier than people that are far away. So somebody at one level of one capability level in basketball may not have anything to do with the lowerly capability. So, yeah, did you get a question, Bill?
No, I'm just thinking something like that.
Yeah. So what's good about that is, my whole idea about physical education and teaching is that you can pair people up and you can exclude certain people from pairing up with certain other people in a very systematic way to get them up to higher levels of performance. So essentially you can stair-step people up to higher levels of motor competence. And this initial study shows that that is possibly what is going on. Of course, we need a lot more data, and these were college students. So we need it with elementary students. That's where we would like to go. Just with elementary students, people tend to freak out when you start filming. Yep.
Did you ever see any particular subjects becoming synchronous with more other subjects?
If you look back, one synchronized with a lot of people, and he particularly synchronized with girls. So there was a little suggestion that there was probably sexual tension going on there, and he was trying to associate with them. Even though he did not have a formal relationship with them, maybe he was trying to work out a relationship.
One does what one can.
Yeah. So, yeah, this is actually pretty interesting stuff, and this one has moved along fairly well. Okay, so do we have any more? Do you guys have any questions? I went a little bit over time.
Yeah, I guess so. Just to jump in one thing you did dribbling. Now let's see. Of course, you'd think that frequency of dribbling would have something to do with height.
Yeah.
Another physiological characteristic.
Yes.
And so from the frequencies don't naturally match, you would expect they're not going to stay phase.
Exactly. Now, if you look at the heights of people that were, because we looked at that, and since they were in the same plane, we knew that we had certain calibration elements, the standardized elements in their view. We actually looked at the height, and it really did not matter. We had short people that dribbled slow, we had tall people that dribbled slow, and that really didn't matter. So it was interesting.
But you can steal from slow dribblers.
You can steal from slow dribbles. And the instruction that we gave them was that you should dribble as if you were going to dribble for the entire day. Dribble at a comfortable pace. And we had certain people that synchronize with others at that pace. Yes.
Just a comment, you could collaborate with the music department and the theater arts
Yes.
department, this kind of
Yes.
thing.
Yes.
They're saying in the community orchestra, and when we lose synchronization, that's called
Yes.
a train wreck.
And a lot of the synchronization research has done clapping of a crowd. There is a certain amount of synchronization there. The big one was lightning bugs. I think there was an entire book written on lightning bug synchronization because the colloquial wisdom was that there has to be some type of central agent that is causing them all to blink at the same time. And they're like, no, and then they started to bring in some dynamic systems theory and say, well, there's no central agent, it's self-emerging as that. So yeah, interesting stuff.
Oh.
Anybody else? 3D analysis, 2D analysis?
Well, yeah, I mean, I was looking at the cameras we had set up in the court, I guess.
Yep.
10 of them, right?
Yep.
Now, they did seem to be focused on the same point.
Yes, and my initial setup, sorry, I have to move the slide. If we look at the initial setup, it was set up to target at the origin. But what we actually found out was that was quite limiting. We have that area, it's only about 4 square meters, okay? But what we found was by tilting this camera out slightly, about 10 degrees, this one 10 degrees, and this one actually about 20 degrees, we were able to expand this quite considerably.
Several foci along the way.
Yeah, quite considerably. We were able to expand this out, I believe we're out at 12 square meters right now. I mean, so a very large area. I can get somebody doing a gate analysis to get 6 full strides across our platform at this point. So it doesn't necessarily have to be focused on that point. Remember when, and the big thing is image error. When you do the dynamic, with the static calibration, the image error is not corrected for. But within that algorithm for dynamic calibration, you actually, they actually correct for those image error issues. And if we weren't doing that, then you would want to try to focus on that sort of point. But it's actually calculating those out. It's actually correcting for the image error. So we don't really care that we're shooting kind of out of the side of the camera.
Can you say more about that image error? I think that's really interesting. We know there is one, but don't know much about
You
it.
get a little bit of parallax error out of just the curvature of the lens. You get a little bit of light issues coming in from the side. Especially, because remember, essentially, this is just 10 two-dimensional views.
Right.
And in the two-dimensional views, if camera 4 and 5 over here have a certain amount of error, when they triangulate, that error is now going to come into any of the calculations that we're doing.
And that's one of the reasons that you're doing the least square fit to find position.
Exactly.
Still, there is this systematic error that has to do with the way the image is formed. I guess we're talking about random. Is there any easy way to understand what that's kind of like?
In either way, it depends on where you put the stops, whether or not. Stops control the distortion from cushion and barrel. And generally, people don't design cameras to get rid of it.
Nope.
It's easy to get rid of,
Yeah.
but hey, don't do it.
Huh. All right.
Or of course, you could go to pinhole cameras, just throw away your lenses. You wouldn't get much light.
You wouldn't
but-
get where, yeah.
But you'd have perfect perspective.
Well, we might be able to have lots of cameras.
But I guess my suspicion is the easy way to do it is just make a really big piece of graph paper and take a picture.
Yes.
You can get
Yes,
for all of it.
exactly.
All right. Well, anyway, I should talk more about this.
I was just curious if there was any like advantage to an optical system of measuring the 3D analysis rather than like if you had radio frequency sensors and a like a GPS type.
And there's actually been a little bit of work into that. Now, with what you guys do, using either accelerometry with some type of radio transmitter, that is, because if you guys are only tracking a single item, a very small system, that's something that you guys can do fairly easily. With the human body, you have to have, no, probably not 35, it would be 16. So you have to have 16 of those with 16 different frequencies. Though it gets a little bit more complex at that point, and then there's some issues that come along with that. And it's basically, because it's the whole idea of an internal system as opposed to a projected system, and that's a big argument within the field.
We're talking about like telemetry, so
Yeah.
these accelerometers that are transmitting data all the time?
Yeah, exactly. So if you were able to, instead of putting 35 markers on, because essentially the 35 markers are just transmitting or projecting a three-dimensional position, right? An accelerometer can do the exact same thing. First of all, you have to be very small accelerometers and be able to telemeter that data. The big thing about motion capture right now is having to get a subject to wear that many markers, and then we've just now got to the point where we can keep the markers adhered. So if you have a dynamic movement, you have to keep all of those markers on that person throughout the dynamic movement. And remember, the computer is actually calculating that three-dimensional skeleton based on all those markers. So when a marker falls off, no more three-dimensional skeleton. So that becomes a major issue. That's why optical flow analysis is going to be so big, because it's got those two-dimensional views, and what they're doing now is they're actually taking those two-dimensional views and they're performing essentially direct linear transformation with those two views to create three-dimensional stick figures with no markers. Okay, and when that comes in, first of all, it'll be extraordinarily expensive. When that comes in, it'll revolutionize the entire field. But then, at that point, I will be able to go into the field, place a set of cameras down, and capture three-dimensional information with no setup time.
You would think that can't be too far away.
It isn't too
All
far
the
away.
different components are sort of there.
It isn't too far away. If you look at like the 3D Connect stuff on, what system uses Connect?
Expects.
What?
Xbox.
Xbox. Xbox is using very similar technology. Now, it's only doing it in 2 dimensions, but they are slowly getting towards 3-dimensional analysis. So it's very interesting stuff that should push it along pretty well.
Do your science students want a summer project?
Because if you can figure that out and you can put a field deployable system together, you're talking a lot of money.
I should think that. Well, I guess since it is about up to 10 of the hour, I think probably we should
I just want to take one question from Jay. He did come all the way over here from kinesiology.
Oh, yes.
Do you think that we could use motion capture, similar to your experiment 4, to look at varying degrees of both arousal and psychological issues, checking for choking, for less rotation?
Oh, absolutely.
Tension?
And what you would do is you do a kind of a pre-post test, and you would actually see what they do normally within practice, and then see what they do within the game situation, and you can actually delineate what are the changes that happen specifically during that. So yeah, absolutely.
Okay.
Okay, well, so.